Thanks. I'm Breandan. I'm a PhD student at McGill. Before I get started, I'd be remiss if I didn't thank the organizers for the great, or putting together this really great workshop. I'm excited to be here and to hear some very interesting talks. So please join me in giving a round of applause for Matthias and Steve. Okay, today what I'm about to share with you is the culmination of a few years of research on a very applied problem. We're interested in syntax repair. We have this tool, and it allows you to take a grammar, context-free grammar, and to insert holes in different places and get completions. So, for example, this does this in real time as you're kind of typing. So if you add a constraint here, it will sort of very quickly update and sample candidate repairs. And it will also work for broken lines as well. So it will suggest minimal valid syntax repairs. I don't want to talk about the tool too much because it led to some interesting theory that we kind of have sort of helped me understand. So what I'll try to do is give sort of the salient insights that got from working on this tool. So just briefly, how does syntax repair relate to context-free languages? Context-free languages are a very elegant theory, and it's very simple too. So you really only need two operators to get this to work. You have addition and multiplication. And so if you redefine these over sets, and you put the string that you want to fix on the first diagonal of this upper triangular matrix, and then you iterate for the fixed point. This is uniquely determined by the entries on the first diagonal. And so if and only if there's a start symbol in the upper right-hand corner, then the string is in the language. And this is if the string is just string literals. But if there are holes in the string, this is where it kind of gets interesting, is that you want to be able to sort of solve for variables. And the way we initially did this was to compile this to a Boolean formula and then solve for the admissible assignments to those variables and then decode them as strings. And this is kind of an indirect way of solving the problem, but it kind of gets the job done. So it checks to see if there's a solution and then output solution, you block this solution to get a fresh one, and you do this a few times until you exhaust all the solutions, and then that's your admissible set. So there's a nice lowering of this onto these bit vector variables. And it's an interesting sort of connection, but it's not very efficient. The way this kind of, if you can visualize how this works, you can do this in the set domain, you can do this in the Boolean domain, or you can do this with variables. With this, we came up with a data structure that allows you to do this over trees. So our initial pass was to encode this as a pair of non-terminals, and for each non-terminal, there's a set of strings that it can represent in this template, in this string template. The issue here with this encoding is that it grows exponentially. You're tracking a very large number of sets of strings as you propagate this through the matrix. Instead, what you can do is a little more efficient, is to represent this as a tree. And so here, it looks a bit complicated, but we can sort of visualize this as a tree, a join, and a merge. And so if you redefine these same operations, just addition, multiplication, then you're computing this over sets of trees, essentially, so forests. And what you can do to sort of make this more compact is to merge the results. So you have unique non-terminals mapped to their productions, and you have a list of productions, so you can have, for each non-terminal, you can sort this list by some statistic. So for example, if you want short strings, you can sort them by the number of epsilons in the string, or epsilon is a kind of an empty terminal. And so we did this. In order to do this efficiently, we built this algebraic data structure. And the way we read this off is that this consists of a terminal or a non-terminal or a list of these trees. And if you look at the kind of Taylor expansion of this, this is the type of all possible, we call them p-trees, or they map onto this bounded length string. And so it's slightly different from a context-free grammar, but it shares some of the same structure in factorizing the productions. And so you have two ways to sample from this tree. Once you construct it, you iterate this fixed point of the matrix, you find the idempotent matrix, and then you sample trees from this. You can do this with replacement, or if you want distinct solutions, which we do, then this method is not as efficient because it will encounter the same tree over and over before it saturates the entire admissible set. And so what you can do is to map this onto integers from a bounded range. And this is kind of a nice way to sample from combinatorial structures that otherwise would be difficult to think about unless you had this bijective mapping. I don't have a whole lot of time to go into the details here, but this was kind of a revelation to me because it's like you can count some structure, you can sample from it, and this is kind of the mantra of analytic combinatorics. There's some details here about denormalization and enumerating hole templates. Where do you put the holes? But it turns out that you don't need to sample for holes either. There's a very nice automata that describes the set of all strings that are within a certain Levenshtein distance. And you can intersect that with the grammar using this Bar-Hillel construction to get a grammar that describes everything that's within a certain distance of a broken string and syntactically valid. Just to mention, this is part of a long chain of work, and we built on top of this, but this allows us to efficiently enumerate solutions in parallel. So the experiment that I think is most telling is that we can scale as you increase the number of cores. You can see Amdahl's law in action here, but you can increase the number of cores to get more distinct solutions. And I'll be happy to talk to you about this at the poster in the session. Thank you.
Thank you so much. All right, I'll take that. Come on up, Sam. Give it a try with your laptop. Let me know this way. Cool. No, we're going to just move on. We'll have questions during the poster session. We're not going to take questions right now. Sorry, guys. Just in the means of keeping things moving.